API 676 is the API standard for rotary, positive displacement pumps. The standard provides design criteria for all types of rotary PD pumps. Under the API 676 standard, there are various codes that define the type of rotary positive displacement pump. The codes are as follows. VR, rotary vane pump with the vane in the rotor versus rotary vane pump with the vane in the stator LS, rotary lobe pump with a single lobe on each rotor LM, rotary lobe pump with multiple lobes on each rotor GET, rotary external gear pump, timed, JU, rotary external gear pump on timed GI, rotary internal gear pump, with crescent, SS, single screw pump SMT, multiple screw pump with additional timing gears SMU, multiple screw pump without timing gears. Screws drive each other. The mechanical seal is the most likely part of the pump to fail. Approximately 70% of the pumps removed from service for maintenance are victims of mechanical seal failure. Mechanical seal parts are highly engineered with very close tolerances, and any upset in the pump or associated system can cause seal failure, including choked suction screen, rapidly closed valves, air or vapor entrainment, misalignment between pump and motor pipe, strained service point far from best efficiency point, hot fluids, abrasives, coking or salting fluids, chemical composition variations, failing bearings, and many more to the power of. Mechanical seals are based on positioning two very flat and smooth discs called seal faces, one rotating on the shaft and one stationary in the pump. Against each other, the discs are flat and smooth enough to almost prevent the pumped fluid from leaking out between them. However, the faces do rely on a very thin film of fluid between the faces to lubricate that rubbing fit. Without this film of fluid, the seals will overheat and fail. Lack of lubrication is the primary cause of seal failure. If the fluid is very hot, it can flash to a vapor as the fluid moves across the faces, again resulting in lack of lubrication. Note that gas seals use a gas film between the faces to minimize face contact and heat buildup. Abrasives can also find their way between the seal faces and wear the face materials quickly. Seal flush plans are intended to keep the area around the seal in the most seal-friendly environment practical, usually meaning clean and cool. Dual seal plans also provide backup and leak detection for safety. Note that seal flush plans use pressure differences at the pump to drive the flush fluids. The pump suction is low pressure, the seal chamber is a medium pressure, and the pump discharge is at high pressure. If you have any questions about which seal plan to use on your application, please contact us. Single seals, basic heat removal, plans 01, 02, 03, 11, 13. and 14. As the seal faces rub together, with their thin film of lubricating fluid, they generate heat. The heat can build up in the seal chamber and push the fluid towards its boiling point, resulting in premature flashing, lack of lubrication, and failure. This first set of seal plans is intended to create circulation through the seal chamber to dissipate the heat out of the seal chamber and back into the pumped fluid. Plan 01 uses passages built into the pump casing to direct fluid flush. Fluid flows from high pressure at pump discharge, through medium pressure seal chamber, and back into the pumped fluid just like Plan 11, but with internal passages instead of the external tubing unusual for modern pumps. Plan 02 isolated seal chamber with no flush fluid moving through seal chamber, has heating cooling jacket built in to add or remove heat from chamber. Fluid used in temperature-sensitive fluids like molten sulfur. Plan 03 tapered seal chamber allows air and vapors to vent away from seal, allows good fluid circulation around seal to remove heat. Common in ANSI-style pumps, very effective and highly recommended for common services. Plan 11 flush fluid flows from high pressure at pump discharge to the medium pressure seal chamber and back into the main flow to remove heat from seal chamber, allows seal chamber to vent on horizontal pumps during initial pump filling orifice. Used to limit flush fluid velocity entering the seal chamber. A high velocity flush can erode the outer diameter of the seal faces. Can be used to increase seal chamber pressure. Increased chamber pressure may be required to keep chamber fluid from flashing to vapor or to provide enough pressure to push the fluid between the faces for lubrication. Seal chamber must be 5 psi minimum above external atmospheric pressure. Very common seal flush plan can be overused in applications where other plans are better suited. Plan 13 flush fluid flows from medium pressure seal chamber to low pressure at pump suction. Best plan for air, vapor, and particulate evacuation from seal chamber. Standard on vertical pumps. Velocity can be limited by using orifice. Plan 14 combination of Plan 11 and Plan 13 fluid flow from high pressure pump discharge, through medium pressure seal chamber, to low pressure at pump suction. Usually used on vertical pumps where increased seal chamber pressure is required, or for ensuring seal faces are wet at startup. Single seals. Flush fluid conditioning. Plans 12, 21, 23, 31, and 132. These seal plans are intended to provide the seal with the friendliest environment possible by cooling and/or cleaning the fluid in the seal chamber. The throat that separates the seal chamber from the main pumped fluid can be further restricted by adding a close clearance bushing in the bottom of the seal chamber, better isolating the cool, clean seal chamber fluid from the hot, abrasive fluid in the pump. Plan 12, just like a Plan 11, but with a filter in the flush line to remove abrasives. Can be very simple or very complex. Simplex or duplex filters, with or without instrumentation. Plan 21, just like a Plan 11, but with a cooler in the line to remove heat, keeps the fluid in the chamber cool. Provides vapor pressure cushion against flashing, reduces coking of hydrocarbons as they cross the seal faces towards atmosphere. Coolers can be water to water, shell and tube, or water to air, radiator style. 1. Pass system. Hot fluid is cooled and sent through the chamber back into the takes a lot of cooling capacity to cool the flush fluid, and water to air coolers often have inadequate cooling capacity. Plan 23, similar to Plan 21, intended to cool fluid in seal chamber, rather than a Plan 21 single-pass system. A Plan 23 is a multi-pass system. Fluid comes from the seal chamber instead of the pump discharge, is cooled, and direct